In this video, we're going to talk about the oxidation states of the main group elements. Now, don't freak out about not remembering what the main group elements are. It's only these in green. We'll cover the others later. Before we move on, you need to make sure that you have a working knowledge of the following: atomic structure, ions, Bohr models, and electron configuration. If you don't have these, it's okay. Go back, look at your notes, and then come back here when you're ready. All right, let's get down to it. An oxidation state, also known as an oxidation number, is the degree of oxidation that an atom's in. Oxidation is nothing more than just losing electrons. We know that atoms can lose or gain electrons. If they gain electrons, they have a negative charge and they're called anions. If they lose electrons, they have a positive charge and they're called cations. A real simple way to think about oxidation state is just the charge. And really, the oxidation state of an atom is just what charge it needs to be the most stable. You should also know that all atoms want 8 valence electrons. This is known as the Octet Rule. So here we have 2 oxygen atoms. The one on the left has 2 more valence electrons than the one on the right. It therefore has a -2 charge, and it's happy about it. On the other hand, the one on the right only has 6 valence electrons. Oxygen is not stable with 6 valence electrons, and it's not happy about it. So oxygen is going to take 2 electrons from somewhere. Kind of like a pirate would steal gold. Oxygen really wants these electrons, and it's going to go around until it finds some atoms who are willing to give up their electrons. What typically happens in the case of oxygen is that hydrogen shows up and says, "Here, take these." After oxygen gets these electrons, it's stable, and in this particular case forms water. While realizing the irony of oxygen sailing the sea to form water is great, not every transfer of electrons is as easy to visualize. Luckily, we have the periodic table to help us. Let's take a look at the second period's electron configuration. And if you've forgotten what the second period is, we're looking at the elements that are underlined here. Here's the list of the electron configurations for all the elements in period 2. You can see that lithium, beryllium, and boron have less than 4 valence electrons, so they're going to lose their valence electrons in order to get a full energy level. This will cause them to have a positive charge relative to the amount of electrons they've lost. Carbon is special in regards to that it has 4 valence electrons. That means it could lose or gain 4 electrons in order to have a full energy level. We're going to say carbon has a plus or minus 4 charge for now. Nitrogen, oxygen, and fluorine all have more than 4 valence electrons, so they're going to gain electrons in order to have a full energy level. That means they're going to have a negative charge relative to the amount of electrons that they gain. Neon already has 8 valence electrons, which makes it a noble gas. It's already stable, so it's not going to lose or gain any electrons. Luckily, this trend continues down the periodic table. Each element in a group typically has the same charge. So the charges shown here can be applied to all the elements in that group. I know some of you are wondering, what about the transition metals? Don't worry, we'll talk about them later. Now that we know that oxidation numbers exist and what they are, let's see if we can apply it with some practice.